Alright, so let's pick up this third part of these notes with some more challenging examples. So these next couple examples are going to be those that do require a system of equations. And so hopefully this will help you if you're still having a little bit of trouble on the last couple homework assignments. The biggest thing that I'm going to do here that might help is we so often last year worked with delta x equals v0t plus 1/2 at squared. Most of the time though, I'm actually going to disregard this and not use that, and instead use the original equation as they've written. The final displacement equals x sub 0 plus v0t plus 1/2 at squared. I hope that as I work this example, you guys will see why I use this one. I do want you to start getting in the habit of doing that, particularly if you have a feeling as you look through an example that this one might be an example where we need two equations. And the reason for that is this is going to allow us to work both of the equations using the same type of measurements. So I do want you to start to get in the habit of using this to where we break up. Rather than delta x, we use the final and the initial. And hopefully you see why as we get going. But let's get into it. So a punt returner catches a football while standing directly on his own goal line. He immediately starts to run, so we'll assume he was at rest, with an acceleration of 6 feet per second squared. Notice it is feet, but that's okay as long as our units are consistent. At the moment the catch is made, a certain individual, we'll call him Jogan Lincolns, is 20 yards away, so 20 yards, so we would want 60 feet, right, instead of 20 yards. And heading directly towards the punt returner with a steady speed of 15 feet per second. A, if neither deviates from the straight line path, where will Jogan tackle the punt returner? B, I took a shot at the fact that it should have been called down, and Jenkins would have been called for unnecessary roughness. So we will just ignore that part. It is, if you were curious, a 15-yard penalty, usually from the spot of the foul, but that's not really relevant. So anyway, let's get into the actual heart of the matter. So we're trying to figure out where, right? We want to find out where they meet, and that's why I want us to break this up. We're looking for what's the final position that they meet at. So I'm going to start this by listing their information separately. I'm going to start this by listing out all the information I know for the punt returner. Right, so for the punt returner, I'm going to list their information, and then for Jogan, I'm going to list his information. Okay, so the punt returner, what information do we know? Well, I'm going to call his initial position, because he started at the goal line, I'm going to call that 0. I don't know his final position, but I'm just going to refer to that as maybe even just x final. Right? I don't know it, but I'm going to refer to it that way. I do know his acceleration is 6 feet per second squared. And I'm going to assume that his original velocity, because the context of the question makes it sound like he definitely started to run. So I'm going to assume his initial velocity is 0 meters per second. So I've got all this information to work with. The only other piece of information that I could really try to look for then would be time, right? So if I look at the time, I don't know anything about the time. So again, I'm going to just maybe call that T1. So the problem here is if I look at this information, I don't have enough variables to work with this, right? I have to think of this kind of collectively as my delta x, but I've only got two pieces of information other than the starting position that I know. So if I wanted to try and just work with this information to either find t or to find the final position, I get stuck, right? I could maybe set up an expression. I could set up his x final, and I almost wrote delta x there, but x final equals x sub 0 plus v0t plus 1/2 at squared. I could definitely set this up, but then I get stuck because I'd have the final position and the time, which I don't know. Okay, so I run into a little bit of a problem, and we'll come back to that in just a minute. Let's also, though, go ahead and list out all the information for our other fellow here. Right, so let's list out all the information for this guy. Well, first and foremost, we know that he's running at a constant velocity, right? And we know constant velocity is delta x over t. But again, I'm going to break that up into the final minus the initial all over t. Okay, so let's list what information we know. Well, we know his final, we don't know his final position, right? But we know that this final position would be the same as this one, right? They're going to be the same thing because that's where they collide. The initial position, right? How far away did he start from the goal line? Well, it told us he was 20 yards or 60 feet. So he actually started at plus 60 feet away from the goal line, right? He started 60 feet in front of the goal line. And then the only other trick here is the velocity. You have to be very careful with the velocity. It tells us he is running at a steady speed of 15 feet per second, but he's running towards the punt returner. So if I'm thinking about this situation, here's the punt returner catching the ball on the goal line, right? He's going to run this way, which I'll define as the positive direction. The other guy is going to run towards him, right? That looks more like a punt returner, but ignore that. This guy's going to be running towards him in the negative direction. So I do need to make sure it is a negative 15 meters per second. It's very, very important we have that negative. Otherwise, if we forget the negative, it's going to be as if this guy was running in the positive direction, and we're curious how long it's going to take this guy to catch him, which is not the situation we're looking at, right? So be very careful with that negative. And then time-wise, time is also important because we know that time so often is the one thing that combines, right? The one thing that brings both of these equations together. However long it takes from the punter catching the ball to running, it's going to take the same length of time for the tackler, right, to reach him and then eventually bring him down to the ground. So I know that both of those times are also the same, which is very, very important. So if I set up these two equations, right, let's start with this one because this one's a little bit easier. I know that negative 15 meters per second equals the final position, which I don't know, minus the initial position of 60 all over the time, which I don't know. So I get stuck here because I have two variables, and two variables means, right, if I ever have two variables, then I better get at least two equations, right? So if I ever get two variables, then I better get at least two equations to work with. Okay, so got this equation, I get stuck, I jump right back over here, and let's start plugging in what we know. Again, I don't know the final position. I do know that he started at 0, so that's insignificant. I know his initial velocity was 0, so that's insignificant. And then I know his acceleration was positive 6, and notice again it's positive because he's, the way that I've defined it, running off in the positive direction. And then I don't know the time, but it is t1, if you will, or whatever you chose to call that, t1 squared. Okay, so I've got this information. Obviously cleaning this up, I get the final equals 1/2 of 6, so 3 t squared, or t1 squared. So at this point, I've got a system of equations, but notice I've got the exact same variables, right? And that's the most important piece. Okay, so now I can bring this all together. If I substitute maybe this in up here, I've got negative 15 equals 3t to the first squared t1 squared minus 60 all over t1. Now at this point, hopefully you notice, right, as I solve this equation, I'm going to get a quadratic. That's okay, we can still solve it, right? Multiply both sides by t1, so I get negative 15 t1 equals 3t to the t1 squared minus 60. When I get everything to the same side, and I put it in standard form just to make it easier for me, I get a quadratic that looks like this. Obviously, yes, you could divide everything by 0, or by, not 0, by 3, because dividing the 0 by 3 wouldn't do anything. So I get t1 squared plus 5t minus 20. And then at this point, it's just a quadratic, so I can either try to factor it, which unfortunately doesn't factor, or I just use the quadratic formula. Now when you use the quadratic formula, you get two answers, but one of them ends up being negative. So we get two different answers. One of them's 2.62, one of them, which I don't recall offhand, but the second one is maybe negative 7 point something, right? The negative time, though, doesn't have any relevance for us. That would be as if they were running backwards in their motion, which doesn't make any sense. So we just figured out here that after 2.62 seconds, that's when they collide. Okay, so all of this information helped us to figure out how long it's going to take. The question did, however, ask us, where will they intersect? Okay, so to find out the position, I'm going to just come right back over here and plug in my 2.62 seconds. So 3 times 2.62 squared, and then when I calculate that, and again this will depend on where you rounded it, but when I calculate that I get about 20.7. Okay, so 20.7 meters. Now the fact that this is a positive 20.7, what does that tell me? Well, that tells me that this is with respect to the goal line, right? So this is a plus 20.7 meters from the goal line. Okay, so we do want to make sure we're keeping track of exactly where we are on the field, or with respect to their frame of reference. Okay, so that's my final answer. That's where they meet. That's how far they made it. Obviously fairly complex here just because it was a system of equations, but if you can define everything in the same two variables, it's not that bad. The other nice thing about this is you should be able to quickly double check. And what I mean by that is if I came right back to this equation, oops, not this equation, but if I came right back to this equation up here and plug in 2.62, I better get something very, very close to 20.7. So if you get something like 20.6 or 20.8, that means it worked. If you get something like 19, then we probably had something go wrong in our solving process. Okay, so it actually is nice that you can pretty quickly double check your answers and make sure they agree and make sure they make sense. But anyway, very complex problem. Obviously, if you have questions over this stuff, come find me. But hopefully this helps a little bit with the system. That problem took a while. This one should be a little bit quicker. So the velocity of a particle moving along the x-axis varies according to the function they gave us. Note that it is measured in our standard units, meters per second. Find the average acceleration and find the instantaneous acceleration. So this example will actually hopefully be a lot easier than the last one, but it does emphasize a very important point. And that point is the average acceleration. That point is the average acceleration. If I want to find the average acceleration, the way that I do that is exactly how I defined acceleration. If I want to find the average acceleration, I just want to know what's the change in velocity over time. Which means even though you might be looking at this and saying, well, if I do the derivative, I could find the acceleration function. For part A, I don't want to do that. For part A, instead, I just want to find out what was my final velocity at 2 seconds, what was my initial velocity at 0 seconds, and then how long did it take, right? Well, 0 to 2 seconds, so just 2 seconds. So to find this, I'm going to find my velocity at 2 seconds by just plugging in, so 40 minus 5 times 2 squared. So in this case, 40 minus 4 times 5, so 20, so 20 meters per second. My velocity at 0 seconds was obviously just plugging in 0, so 40, right? 40 minus 5 times 0 squared, so just 40 meters per second. So if I want to find my average acceleration, so again, this is for the average, and that's what that line above it means, don't forget that. But for the average acceleration, I just take my final, and do notice it's the final minus the initial, and always be very careful about that. It's the final minus the initial. The direction will be very important. And then the change in time, so 2 seconds. So in this case, the average acceleration, negative 20 over 2, so negative 10 meters per second, or meters per second squared, right? The significance of the negative tells me that it is working against, right, the direction of the velocity. It tells me that it's slowing down. Okay, so the biggest theme here, the biggest theme I want you to be comfortable with, when we find the average acceleration, we actually work with the velocity function. If I asked you to find the average velocity, right, if I asked you to find the average velocity, we would actually work with the position function and find those times. Okay, so be very careful when it comes to that. Otherwise, and hopefully you guys are probably okay on that, but that's the biggest thing to make sure you're comfortable with. Part B then is hopefully pretty easy. Part B, I want to find the instantaneous acceleration, and instantaneous information is where we bring in the calculus, right? So if I get v of t equals 40 minus 5t squared, I know the acceleration function is the derivative, it's the first derivative of my velocity function. Okay, so to find the acceleration, I find the derivative. We have talked about integrals now, so just be careful that you're going the right direction with this. Right, when I do the derivative, that cancels out, the 2 comes out front, and I end up with negative 10t. Okay, so my acceleration function is negative 10t, which means if I want to find my instantaneous acceleration at 2 seconds, so my acceleration at 2 seconds would be negative 10 times 2, which is negative 20, right, meters per second squared. So notice on this example here, the instantaneous acceleration does vary quite a bit, right, from the average acceleration. The other thing I want you to think about kind of to end this part of the notes. So the acceleration, negative 10t, is that a constant acceleration or is that a non-constant, right? So the fact that this depends on t tells me the acceleration is not constant. So even though this acceleration makes a straight line, kind of going back to our graphical explanations, the acceleration makes a straight line. Obviously it would be down, not up, but whatever. So let's fix that. If the acceleration makes a straight line, the velocity would be a parabola, which makes sense based on this, which means the x function would be cubic, right? So think about your shapes of the graphs as well. we'll end this part then with that.